Okay, guys, this is getting outrageous. All right, whoever is drawing on my board, seriously, stop. All right? I'm just kidding. All right, let's see. Next question. We had I don't remember where we got. Number 9 apparently is what we're on. And I'm going to try to blast through the rest of this test. And then the next video will be about some of the free response. So question number 9 is asking about a weightlifter lifting up a weight in T seconds, and what is the work that he does? The time is completely irrelevant. Okay? Regardless of how quickly you lift it upwards, the work is going to be the change in the gravitational potential energy. Had they asked for the power of the weightlifter, then that would be option E, right? That would be the work divided by the time, where the work would be mgh. All right, but it just wants to know the work. That's just mgh. All right, so don't be fooled. It will sometimes throw in those distractors just to see if you're paying attention. All right, number 10. So it says we have a balloon here of mass m, and this fellow who's climbing it at a speed of v, and it wants to know about the speed of the balloon. So if the whole system is initially motionless, and then this guy begins to climb upwards, what that necessarily implies is that since it's one system, if you've got one piece of it that starts moving this way, the rest of it has to go the other way, right? If you were, standing on a skateboard, a long skateboard with good wheels so that you don't fall off and look like a goof, if you were to take a step forward on that skateboard, I mean, you guys know it would roll out from underneath you. Okay, that's conservation of momentum, right? If you've got one piece of a system that starts moving this way, the rest of it acquires a momentum in the opposite direction. All right, now, since he is less massive than the rest of the system, that means that the downwards velocity of the balloon will be slightly less than that balloon looks really familiar. I don't know. Okay. Anyway, the downwards velocity of the balloon will be less than his upwards velocity since the balloon is more massive than he is. So, option D. All right, number 11. This is just kind of the classic work done by a force at an angle example. So it's just going to be FD cosine theta. That's all. Okay. Now, had they given the angle from somewhere else, that's the only case where it would have been tricky, right? So it's what is the angle between the force and the distance, right? So if I sort of redraw this, where there's the force, there's the distance, right? All I really did is continue this arrow onwards, right? This angle is this angle. So since it's a dot product, the work done is proportional to the angle between the force vector and the displacement vector. All right, so it is the angle that they gave you. However, if they had given you the angle from the vertical, which would be a mean thing to do, then it would have in fact been the sine function, right? Since it would have been proportional to this angle, but it's supposed to be that one. So the reason it ends up being sine of theta in that case is because if you do something like cosine of theta, that equals sine of 90 minus theta. So if they were tricky and gave you this angle, then it's still supposed to be related to that angle. Right. So if they had said here is theta, then it would have been cosine of 90 minus theta. All right, and therefore sine of the given angle. And again, that's in the event that they switched it up. So as given, it's just FD cosine theta. All right, 12. They make you feel like you're supposed to do something with the 10 degrees. Kind of like this one, that's just a distractor. It doesn't really matter that it's 10 degrees. And they don't tell you the length of the pendulum arm. You could figure it out using, L minus L cosine theta, perhaps. Yeah, but they, oh no, I'm sorry. They do give you the length of the pendulum arm, but they don't actually tell you the mass of the pendulum bob. So there's information missing. But you also don't need the 10 degrees at all, right? They say it's got 10 joules of gravitational potential energy at its maximum displacement. That would be where it's motionless. So that means that the mechanical energy is just 10. So that means that at any position you want to talk about, it will have 10 joules of mechanical energy. So at the very bottom, it would have 10 joules of kinetic, 0 joules of potential energy. All right, so therefore, when the gravitational potential energy equals 5, which is halfway down, that means that the kinetic energy is going to also equal 5 because it's got to add up to 10. All right, there we go. That's 9 through 12. All right, next one, number 13. This is a very straightforward conservation of momentum problem. So, we've said before, don't imagine that every question the AP is going to give you on the multiple choice section is like tricky, because sometimes they're not. They will give you plenty of straightforward ones, right? When you take the real AP, like the first 5 or 6 questions on the multiple choice section are going to be like, if you know any physics, you're probably going to get those right. Some of them are super obvious, right? Others, you have to know some physics. This is definitely in the some physics category, but not tricky by any means, right? So this has momentum, this has momentum. If you do mv for each one, you get that the total momentum of the system is going to be 2mv. All right, so that's the initial momentum is 2mv. The final momentum has to be the same, and since it says they stick together, it's a perfectly inelastic collision. We can just deal with the total mass, moving at some final velocity. All right, so that means that the final velocity is 2/3 of v. All right, so this one's now moving 2/3 of what it was originally. Let's make sure that's an answer choice. Just playing it safe here. It is! We win. Option C. All right, number 14. A lot of the time with this one, people feel like there's more that they have to do, and so they will second guess themselves and think, well, so if I have to slide it up the incline, then I have to, overcome friction. So if it was 300 joules going down, then maybe I have to do extra work on the way up or something like that. Friction is not at all involved in this question. Not even a little bit, right? They say the work done by gravity is positive 300 joules as it goes down the incline. All right? So if we push it back up the incline, the work done by gravity is just going to be negative 300 joules. The work done by gravity, if you recall, is just the opposite of the change in gravitational potential energy. So if gravity does 300 joules of work on the way down, that means that we lost 300 joules of gravitational potential energy. All right, so on the way up, we gain 300 joules of gravitational potential energy. Therefore, gravity does negative 300 joules of work. All right, so that's all there is to that. All right, 15. This one is just a vector addition problem, right? If this vector, and a visual one, right? Not one that involves actual, say, trigonometry, right? So if this right here is supposed to represent the initial momentum of the system, and they are saying that there are no significant outside forces acting on the system, then momentum is supposed to be conserved. All right, so that means that the two arrows that we have afterwards have to add up to this original one. These add up to 0, so it's not A. Right? Those don't add up to this one. These two add up to way more than the original momentum. So the length of the arrow is important. All right. This one, if they had kind of reversed it around, might be a good option. Okay, but this is showing that there's more momentum in the negative direction than in the positive. So, just for the sake of argument, if we had that as an answer choice option, adding these two vector arrows up, they might add up to that one, right? Okay, but that's not what we're presented with. So it's not that one. All right, this one, if you're thinking, aha, well, I know it's not a head-on collision, it's got to be a glancing collision. Yes, that's what we're left with at this point. This one, though, would give us a total momentum in something like that direction, which is not the same. So even if the, say, length added up, the direction would be just out of bounds. All right, so by process of elimination, that leaves us with E. But the reason E is right is because if you add up these two momentum vectors, the vertical components look like they exactly cancel out. Well, that works for this one. It has no vertical momentum, so that works. And if you add up the horizontal components, they just might add up to this right here. So option E is correct. All right. Well, I hope that does the multiple choice section. I'll stop here for a clean break and move on to the free response portion of the practice test.